Now let us look into some of the properties of frequency representation of the signals. Please note that while discussing about these properties, we may consider a continuous time or a discrete time signal or a periodic or non-periodic signal in the sense that we may consider Fourier series or DTFS or continuous time Fourier transform or discrete time Fourier transform. But however, the property that we are discussing can be equivalently be extended to for other frequency representations also. First, we will look into the periodicity property. So, in this property, we will be mainly characterizing the frequency representations. Let us consider a continuous time and periodic signal. In this case, the frequency representation is given as x of t. Sorry, in this case, the frequency representation is given as, say, x of k. Please note that the frequency representation by the nature of it is discrete and non-periodic. Now let us consider discrete time and periodic signals. That is, for a signal x of n, the DTFS representation is given as a periodic x of k. Please note that in this case, the frequency representation is discrete and periodic. Now let us consider continuous time and non-periodic signals. In this case, the frequency representation is given by continuous time Fourier transform. So by the nature of it, x of j omega is continuous and non-periodic. Finally, let us consider discrete time and non-periodic signals. In this case, the frequency representation is given by dTft, and by the nature of it, the frequency domain representation is continuous and periodic. So from these, we can say that if the signal is continuous, if the signal is continuous, then its frequency domain representation is non-periodic, which is obtained by considering these two cases. If the signal is discrete, then its frequency domain representation is periodic, which is obtained by considering these two cases. If the signal is periodic, please note that the frequency domain representation is discrete, which is obtained by simplifying these two cases. If the signal is non-periodic, the frequency domain representation is continuous, which can be obtained by considering these two cases. Now, let us look into another property, that is linearity. So, the frequency domain representation of a into x of n plus b into y of n is given as a into x of e power j omega plus b into y of e power j omega if x of n and y of n are discrete time and non-periodic. From this, we see that the frequency domain representations adhere to linearity property. Now, let us look into another property, that is symmetry property. So, as a part of symmetry property, we will be mainly looking into different characteristics of the signals, that is real or imaginary, then conjugate symmetric or conjugate skew symmetric signal. As a part of this property, we will be mainly considering the continuous time signals, continuous time and non-periodic signal, that is x of t, but the same can be extended for the remaining three cases, that is Fourier series, Fourier series, DTFS and DTFT. Now suppose there is a signal x of t given which is real. That implies x star of t is equal to x of t. Then its Fourier representation x of t is given as x of j omega is equal to integral minus infinity to plus infinity x of t e power minus j omega t dt. From this we can say that x star of j omega is equal to integral minus infinity to plus infinity x star of t e power j omega t dt. But we know that x star of t is equal to x of t itself as the signal is real. From this can be simplified as integral minus infinity to plus infinity x of t e power j omega t dt. So finally we can show that x star of minus j omega is equal to x of j omega. From this we see that the continuous time Fourier transform is conjugate symmetric by its nature. So from this we can prove that, or we can say that if the signal is real, that is x star of t is equal to x of t, its frequency representation is conjugate symmetric. That is x star of minus j omega is equal to x of j omega. Now let us consider another case in which the given signal x of t is imaginary. That implies real of x of t is equal to 0, or that implies x star of t is equal to minus x of t. Sorry, please note that here x of t is considered to be purely imaginary signal, hence real of x of t is 0. So x star of minus t is equal to minus x of t. From this, if we try to find the conjugate of the CTFT representation, that is x star of j omega, we can write that integral minus infinity to plus infinity x star of t multiplied by e power j omega t dt. But we know that x star of t is equal to minus x of t. So this can be simplified as minus integral minus infinity to plus infinity x of t e power j omega t dt. So from this we can show that x star of minus j omega is equal to minus x of j omega. That is, the CTFT is conjugate skew symmetric. From this we can say that if the given signal x of t is purely imaginary, its frequency domain representation, that is CTFT, is conjugate skew symmetric. Now let us consider another case in which the given signal x of t is conjugate symmetric. That is, x star of minus t is equal to x of t. So here we have to find the relevant property of the CTFT of the given signal. So here we know that x of j omega is equal to integral minus infinity to plus infinity x of t e power minus j omega t dt. So from this we can show that x star of j omega is equal to integral minus infinity to plus infinity x star of t e power j omega t dt. But we know that x star of t is equal to x of minus t. So this upon simplification can be written as integral minus infinity to plus infinity x of minus t e power minus j omega t dt. Upon substituting tau is equal to minus t, we can show that x star of j omega is equal to x of j omega. That is, if the given continuous time and non-periodic signal is conjugate symmetric, we can show that its CTFT representation satisfies the property x star of j omega is equal to x of j omega. It means that x of j omega is real. Now let us consider another case in which the given continuous time and non-periodic signal x of t is conjugate skew symmetric. That implies it satisfies the property x star of minus t is equal to minus x of t. So here we can write that x star of j omega is equal to integral minus infinity to plus infinity x star of t e power j omega t dt. But we know that x star of t is equal to minus x of minus t. Upon substitution, this can be simplified as shown, that is minus of integral minus infinity to plus infinity x of minus t e power sorry e power j omega t dt. Upon substituting tau is equal to minus t, we can show that this can further be simplified as minus x of j omega. From this we can show that for the given conjugate skew symmetric continuous time non-periodic signal x of t, its Fourier frequency representation, that is CTFT, satisfies the property x star of j omega is equal to minus x of j omega, that is x of j omega or the continuous time Fourier transform is purely imaginary. So we can summarize the symmetry properties as below. For any generic signal, that is if the signal is real, its frequency domain representation is conjugate symmetric. If the signal is purely imaginary, its frequency domain representation is conjugate skew symmetric. If the signal is conjugate symmetric, its frequency domain representation is purely real. If the signal is conjugate skew symmetric, its frequency domain representation is purely imaginary. Also, please note that if the given signal is conjugate symmetric or conjugate skew symmetric, its amplitude spectrum is even. If the given signal is real, its phase spectrum will have a value of 2k1 pi, where k1 belongs to z. If the given signal is purely imaginary, in this case, the phase spectrum will have a value of 2k to pi plus or minus pi by 2, where k belongs to z. So, from the nature of the signal, we can characterize its frequency representation. Also, it is possible to characterize its amplitude and phase spectrums to some extent. Now, let us consider another property, that is time shift property. So, if the frequency domain representation of a continuous time non-periodic signal is given as x of j omega, please note that this is CTFT. Then the frequency domain representation of x of t minus t naught, which is delayed version of x of t by t naught, is given as e power minus j omega t naught multiplied by x of j omega. Please note that x of j omega and e power minus j omega t naught multiplied by x of j omega have same magnitude, but the phase is offset by an amount of minus omega t naught, which is a power of e power minus j omega t naught. So from this we can say that by time shifting a given signal by t naught, we can say that the magnitude remains the same, but the phase gets shifted by minus omega t naught at any frequency omega. Now let us consider another property, that is frequency shift property. As per the frequency shift property, the signal x of t multiplied by e power j omega naught t will have a CTFT of x of j multiplied by omega minus omega naught. That is, modulating the given signal x of t by e power j omega naught is equal to shifting the continuous time Fourier transform, that is x of j omega by omega naught. Now let us consider another property, that is scaling property. As per the scaling property, the signal x of at will have a CTFT of 1 by mod a multiplied by x of j omega divided by a. That is, compressing the signal in time domain is equal to expanding the signal in frequency domain, or expanding the signal in time domain is equal to compressing the signal in frequency domain. So now let us consider another property that is related to differentiation of the signals. If a signal x of t has frequency representation as x of j omega, d by dt of x of t will have a frequency representation of j omega multiplied by x of j omega. Similarly, nth derivative of x of t, that is dn by dtn of x of t will have a frequency representation of j omega n multiplied by x of j omega. From this we can say that taking the mth derivative of x of t in time domain is equivalent to multiplying x of j omega by j omega whole power n in frequency domain. So far we have considered some of the properties as related to the frequency representation of the signals. Please note that the properties that we covered are shown mainly for continuous time Fourier transform or discrete time Fourier transform. However, these properties can be extended for the complex frequency representation, or sorry, complex Fourier series representation, DTFS, CTFT, and DTFT. Now, let us consider some of the example problems as related to these properties. Suppose there is a signal x of t given as x of t is equal to 2 power t into u of t. Then, 2 power minus t multiplied by u of t. If Fourier transform of x of t is given as x of j omega, then x star of minus j omega is equal to. We know that the given signal x of t is real, that is x star of t is equal to x of t. If x of t is real, we know that its frequency representation is conjugate symmetric, that is x star of minus j omega is equal to x of j omega. So we have to find x star of minus j omega here, which is equal to x of j omega, as the continuous time Fourier transform is conjugate symmetric. Now let us consider another problem in which there is a discrete time signal x of n, which is given as x of n is equal to 2 power mod n, 2 power minus mod n, and it is given that Fourier transform of x of n is equal to x of e power j omega. Now we have to comment on x of e power j omega. We see that the given signal x of n is real. That implies x star of n is equal to x of n. So we know that as the signal is real, its Fourier transform x of e power j omega is conjugate symmetric. We also know that the given signal x of n is real and even. That implies the signal is conjugate symmetric. As the signal is conjugate symmetric, the Fourier transform is real. That is, x of e power j omega is real. From this, we can say that for the given signal, x of e power j omega is conjugate symmetric and real. That implies the Fourier transform is real, conjugate symmetric, and even also, because for real case, conjugate symmetric implies even property. Now let us consider another example in which there is a signal x of n given as 1 by 2 whole power n multiplied by u of n. Now we have to find Fourier transform of 1 by 2 whole power n multiplied by u of n minus 3. We know that the Fourier transform of given x of n is equal to 1 by 1 minus 1 by 2 e power minus j omega. Please note that the Fourier transform here exists as the signal is absolutely summable. We also know that Fourier transform of x of n minus n naught is equal to e power minus j omega n naught multiplied by x of e power j omega. From this, we can say that Fourier transform of 1 by 2 whole power n minus 3 multiplied by u of n minus 3 is equal to e power minus j3 omega multiplied by 1 minus 1 by 2 e power minus j omega. But we have to find Fourier transform of 1 by 2 whole power n multiplied by u of n minus 3. This is equal to Fourier transform of 1 by 8 multiplied by 1 by 2 whole power n minus 3 multiplied by u of n minus 3. From the obtained Fourier transform of 1 by 2 whole power n minus 3 u of n minus 3, we see that this is equal to 1 by 8 multiplied by e power minus j3 omega multiplied by 1 minus 1 by 2 multiplied by e power minus j omega. Now, let us consider another problem related to the frequency representations of the signals. It's given that a signal, discrete time signal x of n is equal to j into 1 by 2 whole power n u of n. Now, here we have to comment on Fourier transform of x of n that is equal to x of e power j omega. We see that the given signal x of n is purely imaginary as it satisfies x star of n is equal to minus x of n. So we can say that x of e power j omega is conjugate skew symmetric. So as the signal is purely imaginary, we can say that x of e power j omega is conjugate skew symmetric. Now let us consider another problem as related to the same. It's given that Fourier transform of a signal x of n is given as 2 power omega. Now we have to comment on the Fourier transform of e power j omega naught t multiplied by e power j omega naught n multiplied by x of n. We know the property that is frequency shift property, as per which Fourier transform of e power j omega naught n multiplied by x of n is equal to x of e power j multiplied by omega minus omega naught. From this, we can say that so where Fourier transform of x of n is equal to x of e power j omega. So as per the frequency shift property, if the signal x of n is multiplied by e power j omega naught n, replace omega by omega minus omega naught to get the corresponding frequency spectrum. So Fourier transform of e power j omega naught n multiplied by x of n can be written as 2 power omega minus omega naught. Here please note that we replaced omega by omega minus omega naught to get the corresponding frequency representation. Now let us consider another problem. It's given that a signal x of t is conjugate symmetric. So now we have to comment on the Fourier transform of x of t, or we have to characterize Fourier transform of x of t based on some property. It's given that x of t is conjugate symmetric, so it satisfies the property x star of minus t is equal to x of t. If this property is satisfied, we know that Fourier transform of x of t is real. That is, x star of j omega is equal to x of j omega. So here please note that as Fourier transform of x of t is real, x of j omega is even. Also please note that phase of x of j omega is equal to 2k pi, where k belongs to z. Now it is given that, sorry, now let us consider another problem as per which there is a signal x of n which is conjugate skew symmetric. If Fourier transform of x of n is given as x of e power j omega, we have to prove that x of e power j omega is purely imaginary. We know that the signal x of n is, if conjugate skew symmetric, x star of n is equal to minus x of minus n. So from this, if Fourier transform of x of n is equal to x of a power j omega, it should be equal to sigma n equal to minus infinity to plus infinity x of n multiplied by e power minus j omega n. So then x star of e power j omega is equal to sigma n equal to minus infinity to plus infinity x star of n e power j omega n. We know that x star of n should be equal to minus x of minus n as the signal is conjugate skew symmetric. So this can be simplified as minus sigma n equal to minus infinity to plus infinity x of minus n e power j omega n. Upon replacing minus n by m, we get that x star of e power j omega is equal to minus of sigma m equal to minus infinity to plus infinity x of m multiplied by e power minus j omega m. We know that this quantity sigma m equal to minus infinity to plus infinity x of m e power minus j omega m is equal to x of e power j omega. From this we see that x star of e power j omega is equal to minus x of e power j omega, which implies that x of e power j omega is purely imaginary. From this we can say that if the given signal x of n is conjugate skew symmetric, that is x star of n is equal to minus x of minus n, then Fourier transform of x of n, that is x of e power j omega, is purely imaginary. Now let us look into other properties as related to frequency representation of the signals. If a signal x of t, which is continuous time and non-periodic, has a continuous time Fourier transform of x of j omega, then the signal minus jt multiplied by x of t will have a continuous time Fourier transform of d by d omega of x of j omega. Please note that this property is corresponds to differentiation in frequency domain. Now let us look into another property, that is convolution property. as per which if a signal x of t, which is continuous time and non-periodic, has a continuous time Fourier transform of x of j omega, if another signal x of t, which is also continuous time and non-periodic, has a continuous time Fourier transform of h of j omega, then x of t convolved with h of t has a continuous time Fourier transform of x of j omega multiplied by h of j omega. From this, we can say that convolution in time domain is equivalent to multiplication in frequency domain. So now let us look into a case in which there is a continuous time non-periodic signal x of t given as input to a LTI system of impulse response h of t. If the output is y of t, which is given as x of t convolved with h of t. So in this case, we can say that y of j omega is equal to x of j omega multiplied by h of j omega. So one way to get y of t is by convolution between x of t and h of t. Another way is find out x of j omega from x of t, find out h of j omega from h of t, multiply these two as shown to get y of j omega, find inverse continuous time Fourier transform to get y of t from y of j omega, which is given as x of j omega multiplied by h of j omega. Similarly, in case of a discrete time signals also, x of n convolved with h of n will have a dt of x of e power j omega multiplied by h of e power j omega. Now let us look into another property, that is modulation property. From this, two signals x of t and h of t, if multiplied at every t, they will have a continuous time Fourier transform of 1 by 2 pi multiplied by x of j omega convolved with h of j omega. Similarly, in case of a discrete similarly in case of discrete time signals also, the product x of n multiplied by h of n will have a dt of 1 by 2 pi multiplied by x of e power j omega convolved with h of e power j omega. So from this from the modulation property, we can say that multiplication in time domain is equivalent to convolution in frequency domain. Now let us look into another property, that is Parseval's theorem. So as per Parseval's theorem, say for discrete time signals sigma n equal to minus infinity to plus infinity, mod of x of n whole square is equal to 1 by 2 pi integral minus pi to plus pi mod of x of e power j omega whole square d omega. That is, the energy in the time domain is equal to the energy in one period of the frequency domain. So this Parseval theorem property can equivalently be extended to for all types of signals, that is for continuous time or discrete time, or periodic or non-periodic signals. Also, please note that in case of a continuous time periodic signal based on alternate Fourier series representation, the Parseval's theorem can be written as integral minus t to plus t mod of f of t whole square dt is equal to t multiplied by a0 square by 2 plus sigma n equal to 1 to infinity an square plus bn square. That is, energy in one period of the signal f of t is equal to squared sum of the Fourier series coefficients as shown. Please note that here the signal m of t is periodic with period 2t. So we have seen the Parseval's theorem in case of discrete time non-periodic signals. We also highlighted that the same can be extended to for any category of signals, that is continuous time or discrete time, then or periodic or non-periodic. We also looked into Parseval's theorem for continuous time periodic signals case, that is through alternate Fourier series representation, which is as shown.